Okay, good afternoon. My name is Natan. Thanks for inviting me. My name is Natan Katz. Do you hear? Yes? And today I'm going to talk about a paper that I wrote together with Uri Itai and published in Advanced Artificial Machine Learning. Why doesn't it move? Okay, so several things about myself. I'm working at Checkpoint since fall 2021. Before that, I spent 3 long months in Avanan. It was a startup that was acquired by Checkpoint. In the last 2 years, in addition to the paper that I'm going to talk about, I was involved in 2 papers about ethics. And finally, I spent, before Avanan, 5 years at NICE. So this is like playing at my home court. I hope that I'll have a good crowd. Okay, so let's talk about the problem. Let's assume that we have to evaluate a binary model. So the steps that we are doing, and we assume that already the model is trained. We just evaluate. So we have test data and model, and we generate scores. We draw graphs, set a threshold, generating confusion metrics. This thing is very trivial. But when we observe the first node of the previous slide, and this here we present the CDF of the distribution. The green is for the genuine, the red is for the imposters. We see this graph, and what we have a sort of a definition of done. Definition of done, by the way, is a term that Gennady taught me somewhere in 2016. There is a product manager that tells us set the threshold to achieve a certain KPI and try to optimize the other, some trade-off KPI, such as if you think about, if Tal discussed here the issue of voice, if you think about voice biometric, the industrial requirement is 1% false positive, so we have to optimize the false reject. I believe that people that work in medical discuss many times sensitivity and specificity, and some people may work with accuracy and precision, but the idea is clear. Set a threshold and bring the performances. Now, when we do this, we are losing a lot of information. And why is that? Because if we observe the curves, the green curve and the red curve, and let's take the horizontal line of 90%, so we see that in the green curve, the 90% point is extremely steep, whereas the red point, the red curve, it is not a plateau, but it is way more stable. What does it mean? It means that we actually set a threshold and we collapse everything besides the threshold. It means that we have no good tool to study the stability of the model, not with respect to changing the threshold variable, and not with respect to different data type. Statistically speaking, we can think about it as we simply don't have a way to estimate a risk or confidence interval or credibility. It depends from which religion you are. Those of you who are familiar with physics may think about here that it's a good place to think about a phase space of the graph and not the state space. But I believe that most of you are not physicists. What is a potential solution? We would like to have something, a good measurement, analytical, and preferably with a closed form. Preferably with closed form in order to be able to derive it. Now, since we discussed binary problems, the best approach is a beta function, because why is that? Beta is a nice distribution with support on 0 and 1, very good for distributions. We use it a lot when we solve, for instance, binomial problems, because this is the prior to bring the P. And what the best thing is that it has a closed form formula for KL divergence. Very complicated, very tedious, but it has a closed form. So this is what do we gain if we use this concept? Now, this is not only the betas, this is the concept. Since beta has parameters, we can assess its risk upon studying the parameters. Since it has a closed form formula, we can derive it and measure its performances in different areas of threshold. And finally, it is endowed with nice metrics over the interval of 0 and 1. The concept and the problem are clear. Forget beta. The concept of the problem are clear? Okay. So if you wish to visualize it, you can think about if green is the distribution of the genuine and red is the distribution of the imposters. And we actually aim to separate them as much as possible. The function in the edges are sort of something that we defined in the paper as the beta epsilon, which mean left beta epsilon and right beta epsilon. These are beta functions that has 0 average, which is nearly 0 and nearly 1. And we actually aspire to push each function towards its ideal function. Now, after I blah, blah, blah about, and was too abstract, I'll present you a checkpoint story where we actually use this. And here there is no Urita anymore. He helped me in the paper. So the problem that we have in IoT is simply we have a traffic of IoT devices, but we know nothing about them, besides the fact that they arrive and the people that record them, the organization, have no way to understand whether these traffics are safe or not. And you have to develop a tool to estimate this. Before we go to the machine learning part, I have to raise 2 caveats about cyber. In cyber, traffic is always in balance because, and I'm not talking about the train set, I'm talking about the traffic that moves around. Always there are machines that comes more, and there are always more benign emails than malicious. It is always in balance, and we always have to capture the best way to do educated guess for what will be the traffic pattern in the production. The other thing that we have to notice is that the traffic is always temporal. Why is that? Because if you think about email phishing or PDF phishing, campaigns are changed. And as they changed, traffic data that was relevant 4 years ago, it's not relevant anymore now. And you have always to try to, the naive approach of doing a split between train and test doesn't always work, and you have to find methods to do some temporal guess. So, and now we back to the IoT. What we know also is that the errors are not similar. Consider an employee in an office that use its mobile either to use a Lutron application in the mobile in order to turn on an air conditioner in the room or send a something to the printer. When it does so, whether we have a mistakes, it's not that crucial. But if one of these mistakes will be done with respect to an unknown traffic, it could be problematic for both ways. We can do an unknown, if you have a printer that we will consider it as an unknown, we destroy the user experience. Again, we worked in NICE. We know very well about synthetic speech and the potential damages that they may cause. And of course, if we think that something that it is unknown, it's an HP printer, it won't be nice as well. So we rewrote the target variables as 1 for unknown and 0 for a device that we know, and moved and converted the function problem to a binary problem. Now I wanted to check the tool, and we had two modus operandis. The first one was to check whether it works well, and the other is to use it for training. So in order to compare it, I use also Matthew coefficient correlation, which is a measurement of correlation between target and true. I have some anecdotes, but I don't have time. And the other was simply measuring the accuracy. So what I checked, I followed the gaps between the distribution after 2 iterations, 12 and 40, and we see that the distributions begins to separate. We need more time, but probably more data as well. The IoT is a poor data project, but we see that the separation begins to appear. when we began to compare, we compared the performances during these iterations. We see that KL diversion grows faster, but it is a bit cheating because KL divergence has different scales than accuracy and Matthew correlation, but we still see that it reacts. Finally, okay. Finally, the last part was adding what we did. We modified the loss function of XGBoost and add this function to the training and see the improvements. And we can see that the upper graph is the without the the upper is in the early training and the lower is in the advanced stage of training. And we see that we can see improvements in all KPIs when we use this function. Thank you.